The stability problem arises because we are using finite precision computer arithmetic to solve difference equations. In these finite difference representations we'll be considering. So these ones introduce rounding errors into numerical solution. The system is said to be stable if these rounding errors are not magnified at each time interaction, so that they're not getting bigger and bigger and bigger, so that the system becomes unstable. So you have to ask the question, if a small error is introduced in the solution, is it magnified by the numerical method or does it decay away? So in case it's magnified, then the numerical method is going to be unstable. And if it decays away, then it's stable itself. So here we're going to analyze, we're going to consider the Fourier approach, which is due to von Neumann. And this is quite straightforward, quite systematic, and quite easy to implement in order to check if the numerical method, I mean the numerical representation, the finite difference representation is stable or not. So the Fourier method, this one, is based on decomposing. Here we are going to justify which are the why we are using that criteria here. But basically, at the end, I'll finally will give you the recipe you have to follow in order to check the stability of the method. But the philosophy of the Fourier method here is based on decomposing the numerical solution into Fourier harmonics. So the Fourier harmonics approximation we'll see next. But we are decomposing that into Fourier harmonics on the spatial grid. Although this method does not capture the influence of the boundary conditions, it's quite easy to formulate and usually accurate enough to provide practical stability criteria. So, which are the Fourier harmonics approximation? Basically, it says that any solution, we can decompose any solution into a Fourier modes in the mesh. So any solution, the u function, particular point n, a particular time j, can be written in this way as a symmetry over m, which are m is a different modes, and the modes have a particular km, which is the value of this km, this parameter is m, which is this index, which is an integer number, times pi over L, which L it's like a total length of the system that we are considering. So the maximum length in the x direction we are considering. So the expression of each mode is the following. We have this function, which is going to be different for different modes and depends on time, on tj. And then times, then we have an imaginary exponential here of I times km that we have said before. That's when defining the mode in the Fourier harmonics times the position xn. So this xn actually is going to be, if we are starting at the 0 position, is going to be n times delta x. And this function, actually, we can write it in this general way. So the time dependence, it will appear in the exponential here. It's a general feature of the linear partial differential equations we are considering. So this is actually the general expression for the different modes in the Fourier expansion for the general solution that we are going to take into account. And as our partial differential equations are linear, we can consider in each mode, each term, this symmetry independently, and that's what we are going to do next. But just before doing that, just keep in mind, it's important to remind you that this exponential of an imaginary number is actually a sum of a cosine and a sine, which I think it's important to have in mind. In general, the exponential of an imaginary number can be written as a cosine of alpha plus I sine alpha. This is my formula, which is actually it's very useful. So every time you have this exponential, you can see that as a cosine plus I times the sine of alpha. So as we have said before, we are going to consider each of these modes independently, but for that we are going to consider that this u function can be written in this way, and the exponential will have I times the k vector, the k parameter times this xn that can be written in this way as in terms of this n index. So doing that, considering each term in this mode, in this sum here, which is what we have to do is the following. We're going to consider that expression whenever we have the specific finite difference representation for a specific numerical method that we have developed. And in order to analyze the stability following that Fourier approach, we're going to substitute that expression here for this uh, mu function, which depends on n and j indexes. We're going to substitute that in the finite difference representation, and then we'll see what's the result of the finite difference representation for this function, for the eta function, this one. And if we see that the modulus of the eta function is bigger than 1 for any k parameter, then will happen that for increasing the j index, for increasing the time, you will see that this, as the modulus is going to be bigger than 1, the parameter will become bigger and bigger and bigger, so that the system or the method itself will become unstable. So if we see that the modulus of this eta function for some k parameter is bigger than 1, then we can say that the system is unstable. So the receipt actually is simple as this one. Once you have the finite difference representation of the method, you substitute the u function by this expression here and check if the modulus of this eta function is bigger than 1 or not. If it's bigger than 1, it's going to be unstable.